So let's go ahead and take a look at a couple of less traditional looking related rates problems. I will try to upload into Classroom a PDF of this, so if people want to see kind of what that is, they can have access to this. Yeah, so anyway, hopefully this is helpful Friday afternoon, so here we go. So I have sand, just like some of those other problems where sand is being dumped out, and it talks about that little bit of a story. But what's a little bit weird about this problem is it doesn't tell you specifically about the radius and the height, but it implies it. So as we go through this story, it says sand is dumped off the conveyor belt at a rate of 2 cubic feet per minute. And I think we've been reading these enough to know now that that means I gave you the dV/dt equals 2 cubic feet per minute. So clearly this sand pile is growing. The sand pile is shaped like a simple cone. The base and the diameter are always proportional, which means if I double the diameter, I would also double the height. Or if I cut the base in half, I cut the height in half. That's it. Or if I grew by 30%, it's 30%. It's perfectly proportional. They go together. So that's very, very important. So as I go like this and I put that in, they're telling me that whatever H is and whatever R is, H over R is always exactly some constant value. Now, when we go through this problem, it says at one point, now this is our snapshot that we talked about, that the height was 12 feet. But they actually said, this is weird, they said that the circumference is 50 feet. Well, the circumference is 2 pi r. So if the circumference, because of course, if it's a sand pile, it's hard to dig through the sand pile and find that, but it wouldn't be very hard to put a string around the edge and find out how far around it is. So if we had that, the circumference is 2 pi r, which makes the radius 50 divided by 2 pi, or in other words, 25 over pi. So if we look over here, that means the ratio of the height to the radius would be 12 over 25 over pi, which in other words is 12 pi over 25. Okay, that's what's going to make this problem just a little bit harder because the numbers are not quite as nice. So let's see what happens. It says, at what rate is the height changing when the radius is 20 feet? So that's again one of those snapshot in time, is we have some idea when it is 20 feet. So let's see. Volume, of course, is 1/3 pi r squared h, but we have a nice little relationship right here that the height, see over here we had h over r equals 12 pi over 25. That means h is 12 pi over 25 r. So that means up here in this formula, I could replace the h with 12 pi over 25 r, or in other words, 3 goes into 12 4 times, so 4 pi over 25 r cubed appears to be a nice simple relationship between the volume and the radius. So that would mean if I wanted to do a little calculus right now, I could say then that dV/dt, if I took this derivative, I would get 12, 3 times 4 is 12, pi over 25 r squared. But again, I'm not taking the derivative with respect to the radius, I'm taking the derivative with respect to time. So we have our given information because they told me I wanted the radius to be 20. They told me that I wanted dV/dt to be 2. So if that's the case, and I plugged in 20, that's really not too bad to go get dr/dt. Now, these are pretty ugly numbers, so I did decide that I was going to go ahead and use some approximations, okay? So let's see what we got. I've got 12 pi over 25. I'm supposed to multiply that by 20 squared, and then I need to take 2 and divide it by that number. It's going to be fairly small. So I got 0.0033. So I got that dr/dt is equal to 0.0033 feet per minute. Okay. Now, unfortunately, that wasn't exactly what I wanted to find. They actually wanted to know how the height was changing. But that was actually okay because based on what I have here, dh dt, the rate of change of the height, would be equal to 12 pi over 25 times dr dt. So all I need to do is take this number that I already have, which I think I'm going to store because I'm probably going to use it again. I'm going to multiply that by 12 pi over 25. And this is, oh, that's pretty nice. So I got that dh dt is equal to 0.005 feet per minute. Now, again, this is a word problem, and we should have some kind of a summary statement saying that that's specifically only at this moment in time. But there we go. We've got that value. We already found that right here. Our radius was here. Now, interestingly enough, that followed up with one last question. It says, at what rate is the circumference changing? Well, we already mentioned that c is 2 pi r, so that means that dc dt equals 2 pi times dr dt. But we already put in here, now, and that's what's also really cool is the radius didn't even come into play. It disappeared with that derivative. So I just need to take 2 times pi, and I need to multiply that by dr dt, which I stored in my calculator as a. So 2 times pi times a, according to this, my dc dt is going to be 0.0208 feet per minute for this particular story. And that's what we got. Now, again, all of this stuff would be predicated on that moment when it is at 20 feet, because all of this is being dealt with that. Because remember, dr dt was found based on that 20. It would actually be something else at a different moment in time because dr dt would change. Okay, so problem number 2. A little more of an interesting look at a Pythagorean theorem question, but we have this observer that is watching somebody. The observer's over here. They're standing 40 feet away from a building. Oh, no, they're 20 feet away from the building. The building is 40 feet tall, and somebody's going to drop a pumpkin off of it. And we are, by the way, it does say we're going to ignore the height of the observer because the observer's eyes will be off the ground a little bit, but we're going to just ignore that for a moment. Now, as it turns out, when you look at this thing, interestingly enough, the height of the pumpkin, so if we call this h from here to wherever the pumpkin is, the height is a function of time. This is a nice little physics problem. You'll notice that the units are in feet. So we're going to use the feet equation. And as it turns out, if you ever use the feet equation, anything free falling, this is from particle motion, in feet is negative 16 t squared. If it's in meters, it's negative 4.9 t squared. Then we put plus our initial velocity times time plus your initial height. This is how you do all of these kind of free-falling questions. But in the problem, it says the pumpkin was dropped. Well, if you drop something, you didn't throw it down, you literally just let it go. So its initial velocity is going to be 0, and the pumpkin was dropped off the building over here, which had a height of 40. So the height as a function of time is negative 16 t squared plus 40. That's the height of the pumpkin. So as we go through this, it says the pumpkin was dropped off the roof, and watch when the height of the pumpkin is 24. So the question that I would have is, when is this height right here specifically equal to 24? Well, I don't think you're going to be too surprised that when we subtract 40 from both sides, I got myself negative 16. Which I rigged this problem to be very, very nice. So I found out that this particular snapshot in time happened when t was 1. Okay, so now what we're going to do is we're going to think about this pumpkin falling. This is h. I'm going to call this z, because that would be how far the observer is from the pumpkin. So I could set up a nice little story, which would be h squared plus 20 squared equals z squared. So of course, when I take my derivative, this was a constant, it's going to go away. We have 2h dh dt, 2z dz dt. That's what I want. And I guess we could cancel out those two 2's, so that's a little nicer. But what I don't have is dh dt. But what's nice about this is dh dt is literally h is a function of time, so dh dt is really h prime of t. And so if I did that, I'd get negative 32t. This was 0, so its derivative is gone. This was a constant, so it disappears. And again, if you take the derivative, you get negative 32t plus 0. So what would be h prime at this particular moment in time would be h of 1 would be negative 32. So I know that dh dt at this particular moment in time is negative 32. So its height was 24 feet off the ground. dh dt was negative 32. Z, oh shoot, I haven't done that yet. We need to figure out what that Z value was at that snapshot. So again, just looking at the story, this is 20. This number right here was 24. Now, again, what I personally really like to do is I like to play little games of special right triangles or just similarity in general. And I notice these are both divisible by 4. So I could call that one 6 and that one 5. Pythagorean theorem 25 and 36. Let's see, did I do that right? Divide by 4? Sure. So 25 and 36 is 61. So this is root 61. So on the large triangle, it'd be 4 roots of 61 would be what I'm calling Z. 4 roots of 60. Why did I say 4? That's 61. And then dz dt. So if you follow kind of how all that works, we have everything that we could want except for dz dt. So I think we'll just go ahead and use a calculator, be a little bit ugly numbers. We're going to divide by 4, and then we're going to divide by root 61. So I'm going to take this, divide it by 4, and then divide by that, and I got dz dt is equal to negative 192 over the square root of 61, and that would be in feet per minute. And that's just all that's happening. Now, when we get to the last little piece, I wanted to find the rate of change of the angle. Well, the angle right here, when you look at it, theta, between the observer and the pumpkin, isn't too bad, because if we thought about it as a tangent, which would make sense, I know a lot of information about this side, and it incorporates a constant, which makes life better. It would be the height over 20. So that would make the derivative secant squared theta d theta dt equals 1/20th of dh dt. But as we've already talked about it, we found out dh dt at that moment was exactly negative 32. So we already have this as negative 32 d theta dt. Now, let's figure out what the secant is. Now, from theta right here, the secant is basically the cosine flipped over, and the cosine would be 5 over root 61. So the secant would be root 61 over 5, but it said secant squared. So what I have is root 61 squared is 61 over 25, d theta dt equals, let's see, negative 32 over 20. I'm going to be a little bit lazy and use my calculator to try to make this work out. I got negative 32 over 20. I'm going to multiply both sides by 25. I'm going to divide by 61, which is a prime number, so that was kind of silly, but I got d theta dt is negative 400 over 61, which negative 400 over 61 is approximately negative 6.557, and this is in radians per minute. Now, again, that's a lot of radians. A radian, like 2 pi radians, is a full circle. That's 6.2 radians. That's more than a full circle per minute. But think about how fast the pumpkin's not going to fall for a minute. It's going to fall for a couple, like literally a couple of seconds. So it's going to go through quite a lot of angle in a very, very short period of time. So in comparison to a minute is pretty crazy. Okay, so let's go ahead and go on to another question. A little bit less typical question, if we will. This is what I have down as my number 3. Now, I've got a rectangle right here that is a rectangle that is going to be circumscribed in a semicircle. So I'm going to try to make this look reasonably good. So here is a nice little semicircle like this. Here is our story. And so what this says is I've got a point, x comma y, that is moving along this circle that, of course, as it moves this way, it's going to get taller, but it's going to get narrower in some way. And so what I want to know is if the point is moving along the curve in such a way that dy dt is half of an inch per second. That means it's sliding up, but also then if it slides up, it's forced to slide over somehow. And it says at a snapshot when y is 1. So again, that's our snapshot. If y is 1, then x squared plus 1 is 25, or x squared is 24, or we could say x is 2 roots of 6 at that plus. By the way, plus or minus 2 roots of 6, because there's one on this side, but also one on that. Now, it actually is asking me a little bit about the area. So keep in mind, if that coordinate is x, then from here to here is x, from here to here is y, but that means this part is also x. So the area would be a rectangle that is 2x long by y tall. So again, that's pretty good. We've got a little bit of information then. And so what we can say then is that A would be, let me actually go dA dt equals the derivative of the first, which should be 2 dx dt y's, plus dy dt times 2x. Okay, so do we have some good information right now? Well, in a sense, we kind of do, but there's something else that I haven't played with that's actually kind of important because I have too much going on here. What I also could choose to do is I could look at this with this lens right here because I haven't played with the original equation. So according to this, if x squared plus y squared is 25, then 2x dx dt's plus 2y times dy dt has to be 0. Well, that means if I brought this across, then x dx dt would be the same as negative y times dy dt. So that's actually kind of a nice little thing that if we wanted to, we could probably choose to kind of move some things around and get rid of some variables. So what I chose to do when I worked at this problem before is I chose to get rid of dx dt and figured out that dx dt is in fact negative y over x times dy dt. So notice if I just divided both sides, that's what I would get. So let's just plug this in over here. So dA dt, which is really what I wanted to find, is equal to 2, but instead of doing a dx dt, I'm going to replace it with negative y over x dy dt times y plus dy dt times 2x. Now that doesn't seem like I did that much, but that actually gave me everything that I needed because I know that for this particular snapshot, y was given to be 1. So each of these y values that is sitting right here and right here is going to be 1. I also figured out earlier that x is going to be 2 roots of 6. So this piece right here and this place right here is going to be 2 roots of 6. And in the given information, we were told that dy dt right here and right here is supposed to be a half of an inch per second. So if you look at all those things that are highlighted, we've got it all, which is nice. So I've got 2
let's see, that would be -1 over x. dy dt was 1/2. Y itself was 1. dy dt was 1/2. 2 from the 2, and x was 2 roots of 6. So it looks to me like everything we could possibly want is sitting right there at our own beck and call. Now, if we put that all together, I will spare you a little bit of the pain of that work, but I believe we get 23 roots of 6 over 12 if we were to try to rationalize that and make that pretty. Or, you know what, if we gave up and just typed it into a calculator, we get 4.695 inches squared per second. So the fact that we're gaining height but losing width ultimately still means in the balance we gained a little bit of area, how that worked. Okay? So hopefully that's a pretty good one. And I thought maybe I would do one more on this video and then I'd call it a day. I have a fifth problem, but I think I'm getting tired and I need to move along here. So for number 4, our last question, we have some parabola. Now notice that, you know, x squared would be a simple parabola down here, but it got scooted up a little bit. So here is x squared plus 2. So there's x squared plus 2. And it tells me that dx dt is 3 meters a minute. So the particle is moving along the curve this way, but as it goes this way, it's going to force it to get much taller. Okay, and it says at 2 minutes, assuming it started out around x equals 0 at time 0, 2 minutes in, the thing has gone over 6 meters. It's a long way. So it's way over here, 6 meters over. So if we plugged in 6, what would that give me? Oh my goodness. This would be way the heck up here at the, again, this is snapshot. It's moving. Again, hopefully that makes sense. 2 minutes, 3 meters a minute. That's 6 meters over. 6 squared is 36 plus 2 is 38. Okay. Now, so for my snapshot, let's figure out how this all works out. It's actually asking me the rate of change of the distance of the particle to the origin. So in other words, I want to know this distance right here, which I'm going to call z just to make life easier. So we're going to have to figure out what the heck is going on. Well, in general, then what I know is that this is x and this is y. So I could clearly say x squared plus y squared equals z squared. But see, unfortunately, that is an awful lot of variables. But we can do something else. There's a few little things that we could do. For example, what I could do is I could replace y right here with x squared plus 2. So I could say x squared plus y squared is z squared, but I could replace y, instead of saying y squared, I could say x squared plus 2 squared. So I think we're pretty much ready to go now because we have the value x is 6. We have the value z. Actually, we haven't done the value z. If we go over 6 and we go up 38, let's figure out that one. I haven't done that yet, huh? So let's see, 6 squared plus 38 squared, and then we're going to square root that big nasty mess. And again, for the sake of time, I could do this in a more precise way, but I'm going to go ahead and do decimals just so I don't have to take the time to simplify all these pieces. But that means I have 2x dx dt's plus, oh no, we have to do chain rule. Let me fix that. Plus, we've got 2 of these x squared plus 2's times 2x, because the derivative of the inside piece, dx dt, is equals 2z dz dt. Holy smokes, look at all that stuff going on. But let's talk about what we know. We knew that x was 6 for this snapshot. So we got that piece, we got that piece, we got that piece. We know what dx dt is because we were given dx dt in the original problem as being 3 meters a minute, right? So we know that piece, we know that piece. And we also know Z because that was, again, our snapshot as being 38.47. So it looks like we have everything yet again. So we can just start plugging things in and seeing what we got. So let's see. We've got 2 of those x's, which was 6, times dx dt, which was 3, plus 2 of those x squared plus 2's, which of course we already figured out was 38, times 2 more of those x's, which is 12, times dx dt, which is 3. So I got 2772 for this whole side. And over here, I have 2 times 38.471 dz dt. And so we can just start doing some division. And it looks like dz dt, it is growing at a rate of 36.027 meters per minute if we are sticking with the units that we were given. And then the last little piece actually asked about the angle between the line and the x-axis, which in other words is this piece right here. So again, not a big surprise. I'm going to utilize a tangent, which would be y over x, but instead of using y, I'm going to use x squared plus 2 over x. Now this is a little bit of an interesting situation because we do have a little bit of a quotient rule at play. So that means the derivative here would be secant squared theta d theta dt equals, okay, so here we go. We're going to do a low d high, which is 2x dx dt, minus a high d low, which is just dx dt, over the square of what's below. Now again, a lot of work there, but again, everything that we have has already been given to us. And so we can grab everything pretty quickly. All of these x's are the number 6. So I have 6 times 12 times dx dt. We have x squared plus 2, which we already knew to be 38, times dx dt, which was 3, and x squared was 36. D theta dt, sitting over here. The secant, again, is the reciprocal of the cosine. So the cosine would have been 6 over root 38, 6 over 38. So this is going to be 38.471 over 6 squared. But again, if you look at it, there's numbers alone here, numbers alone right here. So all we need to do is take whatever this is and divide it by this right here. And I will spare you the details again. You can go through that mathematics, but this is just easy arithmetic with a calculator. And I got theta dt is about 0.069 radians per minute. And I think that should be enough for this particular video. And if you are interested in the last question that I had set up, which talks about this little segment of a circle changing as theta collapses, we'll go ahead and deal with that more on a one-on-one basis if somebody wants to do that. But I will have these problems ready for you guys to work on if you want to, for some extra practice to become better at your calculus. Okay, I will see you back in class. Bye-bye.